Welcome everyone to the HAI Weekly Research Seminar. I'm James Landay. I'm a professor of computer science at Stanford and a faculty co-director and co-founder at HAI. I'm thrilled today to introduce Dr. Carlos Guestrin. Carlos is a professor in the computer science department at Stanford, and his previous positions include the Amazon Professor of Machine Learning at the University of Washington, the Filmmechanica Associate Professor at CMU, and the Senior Director of Machine Learning and AI at Apple after the acquisition of his startup, Turi Inc., which he co-founded. Turi is a platform for developers and data scientists to build and deploy intelligent applications. I feel really honored to have Carlos on the faculty with me at Stanford. We've kind of passed each other a few times in our careers. When he was a postdoc at Intel Research Berkeley, I ran a lab for Intel in Seattle, and then was at the University of Washington when we recruited him away from CMU to UW. And now I'm happy to be here as we recruited him down to Stanford to his home where he got his PhD. So in his talk today, Carlos is going to present us with a framework for driving increased trust in machine learning that's anchored on three pillars: clarity, competence, and alignment. I recently heard a talk he gave on this on the radio. It was really interesting, and I look forward to seeing it in this format. He's also going to cover methods to make the predictions of machine learning more explainable, which is really one of these important problems that is not yet been solved. And before we begin the presentation, I wanted to go over a few logistics. Today, we have the Zoom chat open, so you can message the group. But if you have questions for Carlos, please use the QR code on the screen to ask questions through Slido, or you can click on the link that will be in the chat shortly. I'll be choosing questions from Slido after the presentation, and Slido has a nice upvote feature so that I can choose questions all of you are most interested in. We also have closed captioning enabled for this webinar, so simply click on the CC feature on your Zoom screen to show captions throughout the hour. Carlos, thank you again for joining us. Feel free to share your screen and to begin.
Well, I just raised my hand. Thanks, James. Thanks for the kind introduction. It's exciting to be here as part of HAI. I really believe in the mission and see the amazing things this community is doing. I'm excited to talk to you about the question of how can I trust, or how can you trust machine learning? This is an ambitious and complex question, and I've been thinking about it for a little while. But as James said, I recently joined Stanford, and as part of my application process, I had to submit all the teaching evaluations that I've ever had, and I strategically hit this one. It says, "Professor Guestrin, I'm very disappointed in your class. I thought machine learning was going to be magic, but it's just math." And I call this the math myth of machine learning circa 2008, when I got a teaching evaluation, where we thought that you just took some data, you did some machine learning math, and you got to profit, which at that time meant saying my curve was better than your curve and getting a paper accepted at a top conference. Now, this view is limited, but there must be some magic in machine learning, since we're seeing tremendous impact in the world, from solving open problems like Go to self-driving cars, which are going to transform transportation, to helping us live a healthier day. And to me, the magic in machine learning today is what happens in the spaces between the math. How you define the problem, how you collect the data, how you define your models, how you integrate into an overall system, how you deploy the systems, how you evaluate them in every step of the way. There is math, but it's a small component of an overall system which is filled by complex human decisions. And as machine learning is making more and more decisions for us, and the systems are getting so complex, it's hard for us to understand what's going on. It's natural for us to ask the question of how can we even trust machine learning? And as I thought about this question, I stepped back and tried to study how we thought about the harder question, how can we trust? And I'm very inspired by this work in medicine by Tom et al., where they said that if you have trust in your provider, you have increased adherence to the treatment and continuity of that provider. Well, if you lack trust, you don't seek the care that you need. You don't seek preventive services, which are so important. And you don't seek things like surgical treatments. And they identified 3 areas that are important in the health domain. Technical competency. Does this provider know what they're doing? Interpersonal competency. This provider communicate with me well about what they're doing. And agency. Does this provider have my best interests in mind? I believe these 3 areas of trust are really interesting and really meaningful to what we do in machine learning. And by the way, as a side note, there's a really interesting section in this paper that I think is really elucidating for what we're trying to do here, where it says that trust is different than satisfaction with a provider. Satisfaction is about looking back. This is like saying, my curve is better than your curve in a benchmark data set. Trust is about looking forward. What is your behavior going to be like in the future? This is why in machine learning, we call it generalization. So with this in mind, let's ask the question of what could be the core trust principles for machine learning. And when I think about this, there's many ways we can think about trust, especially in the context of HAI. I can ask the question, how can I trust what I'm building for you? You can ask, how can you trust what I built for you? Or as a community, we should be asking the question, how can we trust as a community what we're building? Are we doing the right thing for the world, for humanity? Now, these are all hard and complex questions. And today I'm going to focus on the first one. How can I trust what I'm building? And how can I empower developers to create more trustworthy AI applications? And to me, there's 3 components to this: the algorithms and methods that we build, how we make this accessible for everyone. These are, to me, open source software is a core component of everything I do with projects like XGBoost, TVM, Lime, GraphLab, and others. And then applications, because I think the notion of trust is really dependent of where you're going to impact the world. And to me, the application domains I've been thinking about recently are all in the healthcare domain. So I'm going to talk about notions of trust along 3 pillars that I think are important: clarity, competence, and alignment. I'll describe some methods, some places where we can make a difference. And for each one of them, I'll describe an open research problem that I and others are working on today. So let's start with clarity. Clarity is really the notion of being well understood. As a machine learning person, I can be summarized by a very simple equation. If you give me some function to optimize, I'll stay up all night, I'll forget to eat, I'll forget to do anything else, but I'll make F as big as possible. And this is where the mistakes start. Let's start with a very simple user study with all of us, which I'd love to have done in person with you, but helps clarify these notions that we're talking about. So back when I was at University of Washington, the mascot for the university was a husky. Every time there was a game, we brought a husky to the stadium. But there was a really problematic issue. What happened if we brought a wolf instead of a husky by mistake? Maybe thousands of people could die. Now, you might think this is an exaggerated problem, but no, it's a real problem. Now, we got together with the senior leadership and we decided to take the very natural path of using a neural network to predict if what was coming in was a wolf or a husky. And the decision was, if this model meet our accuracy criteria of 95%, then we were totally happy. That is, if in 1 in 20 games, we brought a wolf to the stadium and we risked the lives of thousands of people, then that was okay. Of course, this is a joke. But the question is, we built a model, if it meets this metric that we think we care about, my question to you is, would you trust this model? Is that enough for us to be satisfied and deploy this in the real world? Now, this is a hard question. In the standard machine learning practices, if you read a textbook or if you take a machine learning class from people like me, you'd say, if I meet my accuracy requirements, then I'm done. I can move on. But if you dig in and you start looking at your data, which is what I tell collaborators, students, folks that I've worked with to always do, you can start seeing that the metric that you try to evaluate might not be good enough. And there are many ways you might want to do that. One way to do that is with explanations. So my former student, Marco Ribeiro, came up with a way of trying to understand what parts of the data were important for making a prediction. In this case, when I was predicting this image to be a husky, the parts on the right were the parts of the image that were important. Then you can see for these different examples, what parts of the images the model was looking at. And if you look at the ones that were classified as wolf, you'll notice that we don't have a wolf detector. We have a fancy, very deep snow detector. In other words, there's spurious correlations here. The pictures of wolves were typically taken in snowy conditions. And so the model was fixating on issues that were not necessarily relevant, especially in Seattle where it doesn't snow that much. So going back and thinking through, is this model really achieving the metrics we're hoping for the right reasons, is an important aspect of everything we need to do in this space. Now, if Socrates said, as reported by Plato, that an unexamined life is not worth living, I would say that Marco would suggest that an unexamined model is not worth deploying. And so clarity is really that question, the question of being well understood, the question of understanding where this model is doing things for the right reasons. One way of doing that is by thinking about interpretability. And to me, interpretability is about giving a human a mental model of the behavior of the machine. One way of achieving interpretability is by using very simple models, like a simple decision tree. Now, these are very highly interpretable, just a few if-then rules, but the challenge is that the accuracy tends to be very low. We can try to make them more complicated and more accurate, but now you have spaghetti code that's very hard to understand. And real-world use cases require more complex models, more accuracy. There's a field of research trying to make simple interpretable models more accurate, but they often don't achieve the real-world use cases and the superhuman intelligence that we see advertised and promised for AI. And so my question is, can we increase the interpretability of this most complex, most accurate machine learning models? And the way we approach this, and we started a few years ago, and now there's been thousands of papers and follow-on work showing how to do this even better, was to say, let's not look at the internals of the model, but let's consider it a black box. We call this model agnostic explanations. And if we can do that, we can explain any state-of-the-art model. We can explain existing and future models that somebody will come up with, and we can compare models from different model classes, even ones that haven't been invented yet. Now, the decision space of machine learning model might be very complex. And the insight that we had in the first approach here was that if you take a particular prediction you want to make, and you zoom in, and you zoom in some more, the decisions might be locally simple. And in line, at first endeavor in the space, we said, can we fit a simple linear explanation around each prediction? And it turns out that this was already a very powerful insight. So take this confusing image for an image classifier. If you use the simple approach, it will say it's an electric guitar, with probability 32% when it's looking at this part of the image. It's an acoustic guitar when it's looking at this part of the image. And it's a Labrador when it's looking at this part of the image. So this gives us some insight as to how the data relates to the predictions the model is making. And when you have alternative predictions or uncertainty, it helps associate different parts of the data with different predictions or decisions you might make. Now let's go back to the husky example that we did in the user study. We did a much more formal user study with 27 subjects who were senior graduate students in machine learning. And we did a more formal version of what you did. And more than 60% of them didn't trust the model when we started off, basically because they didn't trust me. And about 40% had this no insight. They understood this no as a spurious correlation. After seeing the explanations, 25 out of 27 no longer trusted the model, and 26 out of 27 had this no insight. So my question to you is, who is that person who had this no insight and still trusted the model? I don't know, it's a double-blind study, but it's an interesting question to go explore further. So interpretability is about giving humans a mental model of the behavior of a machine learning system. Lime used the simple insight of local explanations or local decision boundaries as a way to try to provide explainability. And there's been a lot of follow-on work where other notions of explanations, other ways of doing this have been proposed, and they all provide different insights into the behavior of machine learning. That's really exciting. As a motivating example for what's coming later in the talk, as another example of explanations, here's some work that we did that we call anchors. Rather than finding a locally linear explanation, we try to find sufficient conditions to keep the explanation the same. In other words, what is the space that we could perturb the input and the decision doesn't change? So for example, for this image here, the model predicts as a beagle. If you look at this part of the image, no matter what happens in the rest, the model will still predict it as a beagle. And you can apply this in interesting ways. Take this amazing task. It's called visual question answering. You give me this interesting image and you ask the question in natural language, what's the mustache made of? And it says banana, which is pretty impressive. Or you ask it, how many bananas in the picture? And it says 2, which is also pretty impressive. But now, if you ask what the anchors are, for the first question, the anchor is what? For the second question, the anchor is many. That is, for this image, any question of the word what gets the answer banana. Like, what's the ground made of? Banana. What's hair made of? Banana. What was the head of the US? Banana, and so on. In the second question, any question of the word many gets the answer 2. Like, how many people in the picture? 2. How many is too many? Obviously 2. So what we see is, even though it seems like the model is performing some incredible analysis task, there is some brittleness in the space that needs to be explored further. And providing this clarity and understanding of the behavior of the model gives us insights into how the models behave, what the models might break, but also helps humans make better, more informed decisions based on the predictions of the model. I think about this as not AI replacing humans, but the augmentation of human intelligence through AI. I believe that not just predictions, but predictions plus explanations and justifications can help people make better decisions supported by AIs. And we see that with each other. Somebody suggests something, you may or may not take it on, but somebody suggests something and explains why it might be good for you, then you might be more inclined to take that advice. And this idea, following on the work that we propose, has been explored in interesting ways, not just by us, but by others. So for example, this really interesting paper that I was not part of showed that you can help doctors detect hypoxemia during surgery by a combination of machine learning model with explanations. And we're exploring this in the health space in really interesting ways here at Stanford. So for example, a question that I'm particularly interested in is, can we make better decisions by combining predictions plus supporting evidence? So in work with Emily Fox, Ramesh Johari, David Mas, Priya Prahalad, and David Shankar, we're looking at type 1 diabetes management, where somebody's blood sugar might go up and down over the day, depending on a number of factors, like what they're eating, carb intake, what insulin their body is producing or they're injecting themselves, and activity that they do. Now, the standard of care for type 1 diabetes used to be prick your finger to measure glucose level and inject insulin manually. With the advent of wearables called continuous glucose monitors, you can put a patch and measure your glucose level over time in a continuous way. And it's really, really interesting as a technology for scaling up medicine and providing better care for the people with this condition. Now, what David Maas and Priya Prahalad from the Children's Hospital have shown is that by combining continuous glucose monitors with telemedicine, they're able to help patients stay in a target range better than otherwise, which is great. And somebody looks at their data every week. It's called a Certified Diabetes Educator, or CDE, looks at the data every week and provides recommendations in terms of dosage changes or lifestyle changes. This has been an incredibly great study with a lot of potential. And the question that I'm really interested in is whether we can help these interventions that somebody might make be more explainable. So not only say that you have a point where you have hypoglycemia, your glucose level goes too low, but through some annotations like, this is when you went to soccer practice, you're able to better understand whether some intervention might make sense. In this case, rather than decreasing the insulin calibration, we can say, look at this part of the data, look at the behavior that somebody changes. What you might want to do is reduce the insulin before you go to soccer practice and have a small snack during practice and stay further in range. So combining explanations and decisions, I believe, can lead to better care in a number of different healthcare situations. Now, we talked about clarity, the property of being easily understood. The second area of trust for me is competence. Competence is the quality of having sufficient skill, knowledge, judgment, strength for a particular task. In machine learning, it's really about having sufficient skill for a particular duty. Is about evaluation. Is this model good enough? In 2008, the question was really simple. I could say, my curve is better than your curve. It's sufficient to get my paper accepted, as evaluated on a benchmark data set. But even this notion of a fixed test set is extremely naive in practice. What I believe we need to take is a more software engineering perspective to how we do machine learning. Really think about an entire QA process. Do things like failure analysis, systematic testing of the models that we do. Let me share a couple examples of that. The first one is what we call adversarial bug discovery. So in other words, how can I perturb my data a little bit and break the predictions of the model? This has been studied before we endeavored into this in really interesting ways. Like you take this image where a model predicts it to be a panda, you add a bit of imperceptible noise, and now it predicts it to be a gibbon. Now, this is adversarial perturbations that are really interesting, and they might be useful for, say, security attacks, but to me, they're not really bugs in the sense that they're not distinguishable by humans. They're not the kinds of bugs that the user will perceive. But let's look at these other kinds of problems. Take this image, you ask the question, what type of roadside is shown? It says a stop sign, that's impressive. Or give me this paragraph and you ask the question, how long is the Rhine? It says 1,230 kilometers long, which is pretty impressive. However, if you change the first question from what type of roadside is shown to which type, now the answer is do not enter. Or if you change the question from how long is the Rhine to how long is the Rhine by adding an extra question mark, now it's 1,050,000 long. These are perturbations that you naturally see in the real world. They're breaking the models in very problematic ways. So can we find this, what we call semantically equivalent adversarial examples? And we did this in a very simple way, combining some paraphrasing models and finding out where the models break. And you get really interesting behavior, like this one. You give me this image and you say, what color is the tray? It's pink. You find some paraphrasing like, what color is the tray with British accent? And now it's green. Or which color is the tray? And it's now green. And by finding this natural perturbations, we're finding places where maybe there's enough coverage in the data, or maybe there are issues that need to be addressed. And this can help create a feedback loop to make models more robust. So for example, in different tasks, just by finding these adversarial examples and very simple data augmentation based on them, we're able to significantly increase the robustness of machine learning models. Now, these machine learning models are prone to bugs, and we need to really understand what these issues are and find ways to address them that are meaningful for the task. And some of these can be captured in the data, like we talked about, but some of these are more complex and hard to really understand where they're coming from. Let me give you an example of that. So take this image, you ask the question, how many jets are in the picture? You get 6, that's impressive. But then you ask the question, are there 6 jets in the picture? And the answer is no. Just having a test set doesn't capture these inconsistencies that a model might have. So being able to evaluate whether a model is consistent or not is another example of the kind of robustness we're hoping for in machine learning models. In this case, the issue comes from the fact that although there were about 13% of the answers in the data set with numbers, only 0.3% of the questions had numbers. So the models didn't really learn to answer questions with numbers in the question. And it's really hard to collect a fully general data set. One way of doing this is identifying this problem and collecting more data. But there are many other things that we might do. Just as a small suggestion, we show that one of the things we might do is another form of data augmentation. For example, if you ask the question, when did Trump become president, 2017, you ask the question, can transform that question into who became president 2017, Trump. And just with very simple natural language constructs, you can augment the data by rephrasing different ways questions and answers could be generated, by changing subjects, changing the direct object, and so on. And you can generate a large number of transformations that increase the coverage and robustness of your model. So it doesn't change the overall quality of the model on the left columns here, but increase the overall consistency of the approach by just doing perturbations. So overall, we need to explore new ways of increasing the coverage and robustness of models, not just through collecting data, but through understanding the semantics and properties of the domain at hand. Now, even if we do that, and even if we do all this testing, debugging work that we just talked about, you might ask the question, when are we really ready to ship this model? When do we feel like we're done? And our hypothesis here is that we have to learn from software engineering. We have to test models like we test software. So last year, we came up with a methodology we call checklist for more thoroughly testing these machine learning models. So let's take a simple example of sentiment classification. Take an input like easily the best airline in Seattle. Wait, I should rephrase that. Easily the best airline in San Francisco. You give that to sentiment classifier, and you should say this is a positive, negative, or neutral sentence. If you're software engineering, you'll have some testing practices that you'd implement, like unit tests, test small units of software. You look at different types of small units. In this natural language setting, might be vocabulary, named entities, negation, and so on. You'd come up with a number of tests that you think are important. You'd evaluate your software amongst those tests and get some checks and crosses. And when you think that performance is sufficient for your task, you say you're ready to ship. And this methodology needs to be more thoroughly applied in the machine learning domain. And this is what we did with checklists, create such methodology. And show you a few examples of that. The first one is what we call minimum functionality tests. You can think about this as unit tests. This is like the simplest thing you could possibly imagine. If you fail this, you shouldn't be shipping. Like, give me a polarized sentence, it should say it's polarized. So if I say this, I despise this aircraft, you should say this is a negative sentence. Or a negation. If you find a negated negative, then it should be either neutral or positive. Like you say, this food is not bad. So just identify some sentences like that and make sure your model passes this test before you ship. Now, despite being so simple, if you look at state-of-the-art models or public APIs where you pay money for, they fail at the very simple polarized sentences at rates of up to 15%. And with negations, they fail at the rate of up to 50%. And that's a problem. Another kind of test that is typically done in software engineering is metamorphic tests, which we call perturbation tests or property-based tests. And these are testing invariances in the model. So here's a very simple thing. If you have say a location and you change the location, you shouldn't change the sentiment. So if you're saying I'm going to fly to Chicago and I'm flying to Dallas, I say probably you shouldn't change your sentiment. Nonetheless, public APIs or state-of-the-art models fail this at rates of up to 20%. And another kind of perturbation is directional tests. So for example, if you add a negative sentence on top of a negative sentence, like your service sucks, you're lame, that should make it even more negative. But public APIs failed at rates of 30%. So these are very significant problems that I believe are due to lack of systematic testing of machine learning systems. And what we came up with is a methodology for making it easy to create such tests and deploy them in real systems. In a user study based on practitioners and people who are actually deploying models in production, we showed that by using the methodology checklist and by using checklists in the tool, they're able to create more test cases per test category and find more mission critical bugs than without these systems. So competence, the ability to have sufficient skill for the task at hand, understanding where you fail and not fail, and thoroughly testing is, I think, a second key component to gaining trust in machine learning systems. And really understanding how to make these competent models, I think, is a really important part of what we should be investing time in. Here's another example of research question that I'm interested in. How do you teach a machine learning model a new capability? Let's say that we have a personal assistant, and now you want it to answer questions about human-centered artificial intelligence. It's never seen questions like that. How would you go about solving this problem? In a standard textbook, it's pretty easy. You have some training data, you give it to the model, evaluate some test data, and you're done. Now, you can imagine you don't have training data in this case. What are the questions about human-centered AI you might want to answer? There's no training set and test set. If you think about notions like few-shot learning, they still assume you have a very large test set to know that you're done. But in practice, how the systems are built, somebody's defining this notion. We have to answer questions about human-centered artificial intelligence. They maybe come up with some data by hand in an ad hoc way. They train an initial model, they build a prototype, they do some failure analysis, maybe they collect more data, maybe they ship it, they come up with a new version, they try to understand when it's working or not working. There's a whole cycle that can be very ad hoc and hard to understand. And some of the parts of the cycle, like how do you define what it means to answer questions about human-centered artificial intelligence? What do you mean by that initial sample data set? How do you know there's enough coverage? How do you understand what is working, not working? How do you know what more data you need to collect? This outer loop of machine learning has not been studied as thoroughly as the inner loop of optimizing model performance. And I think it behooves us to think carefully about what the entire machine learning process looks like to build more trustworthy models. So while competency is about having sufficient skill for the task at hand, and clarity is just this quality of being easily understood, the last area of trust that I think is really important is alignment. And alignment is the state of agreement or cooperation between persons, groups, nations, etc., with a common cause or viewpoint. And the key machine learning here is the common cause or viewpoint. In 2008, the common cause or viewpoint was very simple. Get a paper accepted, get tenure. But in reality, there's a huge gap between what a machine learning model is trying to do and what you really care to do for the real world. Netflix demonstrated and talked about this really in interesting ways. In 2006, they proposed a Netflix challenge where they put out this really interesting data set, which led to a large amount of work on recommender systems. The task there was to predict the rating that somebody would give to a movie. And they'll measure the error in terms of sum of squared errors. Although this was really interesting, brought a lot of visibility in machine learning to Netflix and led to a ton of work in recommender systems. It wasn't applied directly in Netflix as reported by them, because what they really cared about was minimizing the probability that a user would churn next year, not predicting the rating of a movie. And through practical experimentation, they noticed that a better machine learning metric was what is the probability that you'll binge watch something? So what's the probability you'll click on something and watch it to the end? And if you maximize that probability, then a user was less likely to churn, and it was something that was easier to optimize. Now, what I call this gap between the business metric that you really care about, or the product metric, and the machine learning metric that the engineer optimizes, the loss metric mismatch. You can solve this by picking a better loss function, so maximizing the probability of binge watching as opposed to some squared errors on ratings. Or you can find better approximations of the metric. They're easier for machine learning to optimize. But fundamentally, there's a organizational problem here. The product metric are usually owned by product managers, by the business. They're very complex and they're long-term. Or the loss function is what all a machine learning engineer sees in their day-to-day operations. And closing this gap can be very complicated. A small step in this direction that we took when I was at Apple was to say, let's find a parameterized family of loss functions. And then as you're optimizing the parameters of the model, every so often we evaluate the business metric we really care about and use that to go and update the parameters of the loss function to bring it a little closer to the metric we care about. We call this adaptive loss alignment. And the simple technique was really important to improving the quality of the Face ID feature of how you unlock your phone based on face recognition. But this is a small step of a really big problem, this gap between what machine learning models try to optimize and the thing that you really care about in the real world. And with the advent of large language models and foundation models, you're seeing this gap getting even longer, because now we have the foundation loss that was used to train the model or the language model. There's the prompting that you do, and there's the metric that you really care about, increasing this distance of separation, and will make this problem even more significant. But even this notion of having one metric that you care about, as we saw, it's limited. You have really multiple areas that we need to evaluate the model, and it can be conflicting with each other. And alignment here is really about balancing the concerns of the application that we have or the values you want to exhibit. Here's a very, very simple example of that. One of the features that my team shipped at Apple is called Raise to Speak. Instead of having to say an activation word for something like Siri, you could just, on your watch, you could just raise your arm and say, what's the weather today?
It's currently clear and 63 degrees.
Yeah, California. So instead of having to say the activation word, just based on gesture and voice, you'll be able to figure out what the user's intent is. And there are different kinds of errors you could have. So false reject is when you do the gesture, but Siri does not get it. So this is kind of a missed gesture. A false accept is like, you're Latino, you're speaking with your arms, and then suddenly Siri interrupts you. This is a really annoying interruption that makes Siri feel really, like a stupid device. And so how do you think about the trade-off between the two? The way we thought about this is to say, we only want one of these interruptions, say every week, but minimize the number of false rejects based on that. So you come up with a bunch of different models to trade off false rejects and false accepts. You pick an operating point that you think is right for the user experience, and that's what you execute. So this is one kind of trade-off, but ultimately is about the alignment of multiple criteria to meet the values they want to exhibit. And with machine learning, we know that this issue is really complex. Issues of algorithmic bias have been well documented, having significant impact in the world, negative impact in the world. And there are incompatible fairness criteria that we might want to try to optimize. So how to balance the trade-offs between multiple metrics that you care about, it's really difficult. And ultimately, every choice that we make in the development of a machine learning model needs to be aligned with the goals of your system. And we need to be really thoughtful about this. So for example, I ask myself the question all the time, what am I teaching these machine learning models? Or what am I teaching my kids? So here's a picture of my son and daughter some years ago, watching a show that they love and I hate called Paw Patrol. In the show, there's 6 puppies that go on life-saving missions. There's only one girl puppy, Sky, who is usually dressed in pink, watching the sidelines while the other 5 puppies save the day. This is clearly not the example that I want to give my son or daughter. Now, as we're increasingly experiencing the world through devices, filled with machine learning powered experiences, we have to be careful not to perpetuate such biases. And every choice that we make in machine learning, every choice we make in the data has impact in the models and what they exhibit in the world. This is not new. In the 40s and 50s, when Kodak had labs across the world and film was developed using chemicals, they need to calibrate these chemicals to make sure they had good quality of pictures everywhere. So they created these cards, they call Shirley cards. You can see a little bit of sexism right there, that were used for calibration, and they always had a picture of a fair-skinned female model in them. So for folks with lighter skin tones, the pictures always look great. But for folks with darker skin tones, pictures are always overexposed. And you can really see this difference when you look at pictures with folks with lighter and darker skin tones in the same image. And it wasn't until the 80s and 90s when cards with images of people with different skin tones were used for calibration. Now, diversity or coverage in the data is really important, but we really need to make sure that every decision that we make in the development process exhibits the values we're hoping for. And this can be really, really difficult. So for example, take machine translation. With neural machine translation, we can do amazing things, translate amongst hundreds of languages. But we can also be faced with very complex problems. For example, if you translate from a language like English that's non-gendered to a gendered language like a Latin language like Spanish, Portuguese, or French, and you say, take the sentence, the doctor called the nurse, it gets translated into the male doctor called the female nurse. Now, in Brazil today, about 57% of doctors are male, though the ratio of female doctors is increasing rapidly. If you make a hard translation choice, like we did, even if you had infinite representative data, you won't solve this issue of perpetuating biases that doctors are males and nurses are female. So we need to think carefully about how to exhibit the values that we want to exhibit, to not perpetuate the stereotypes, but also deliver a great user experience. And this is a really hard question. So alignment is really about considering the consequences of every decision, every action that we take on the machine learning system that we build. And how to translate your values into the metrics is a really hard, challenging task. Typically, we're optimizing multiple metrics at the same time. And as a machine learning practitioner, we know how this works. We put lambda 1 plus lambda 2 plus lambda 3 and plus lambda 4 and so on. And that's what we optimize because this is the simplest thing to do. But implicitly, these lambdas are representing trade-offs. They're really hard for us to evaluate. And thinking about what is the human in the loop process to really understand from a human perspective, what is the impact on values for these trade-offs that we make is a really hard set of decisions that we need to make more transparent, more clear, more effective. So I believe that by focusing on clarity, competence, and alignment, we can build more trustworthy machine learning systems and address the question of how to have more positive impact in the world. Thank you so much for your time today. I really appreciate you being here with me, and it's really a great experience to be engaged with HAI. So thanks, and back to you, James.
That was a super great talk there, Carlos. And we have a whole bunch of different and interesting questions in the Slido, and you can still ask them there or upvote ones that you think are great. But I'll start off with the first one that has a lot of votes. From Muffy Waterman, is there a standard practice of disclosing the data upon which a model is trained?
The answer to that question, so the question is whether there's a standard practice for this. The answer is no. Most companies, as far as I know, and even governments don't disclose exactly what data was used for training a model. And in fact, one of the things I've observed in practice is that many companies have a hard time keeping track of the provenance of machine learning models. That is, for the current model that's shipped in web service or in a device, what was the exact data versions, what were the annotations, what were the parameters that are used to create that particular model? Because there's so many steps on the way, the provenance question has become opaque often. So this is something that requires better overall systems and processes in general. I think some companies have been doing a good job at this, but in general, I think it's an open problem.
This one's kind of a pretty open-ended one, so we'll see what you say here. What do you think is the biggest barrier in creating more explainable models and deploying them in industry?
That's a great question. I'll answer a slightly different question to it because it's so open-ended. But when we came up with Lime some 5 years ago, our approach to this was, here's a question of how to make models more explainable. Here's a tool that we had in our toolbox, and we created a system, and it got a lot of usage, and it's great, and there's been so many papers. But we made a fundamental mistake when we did that paper, in my opinion, looking back 5 years. And I'm trying to do things differently these days. And James would not make this mistake. We didn't start with the question, what is the decision that a human is making and what is the explainability that's supporting that decision. In other words, we try to make predictions explainable, but we didn't turn it around and make the subtle distinction to ask what would be helpful for whoever is taking that decision into account. So now that I'm looking at healthcare, for example, I'm thinking a clinician is making a decision, or a family is making a decision, or together making some decisions. We might want to ask, what is the data that supports that particular decision, and how can we do that better? And I think one of the biggest open questions in my biased opinion right now is how to bridge that gap, how to make explanations or explainability machine learning actionable for whoever's consuming them. So that's one of the points that I'm thinking about quite a bit right now. But I can continue on this one because it's more, but I don't know if you have more questions.
We have lots of questions. Let me give you another one. Is really about scalability. So Pete says, some of these methods, i.e. annotation, seem really effective, but do you see them as being extensible to larger scale models, or are there alternative methods you would need to use there?
I think that this is a great question, and I've worked on scalability machine learning for a long time, so somehow that's always been on my mind. A lot of what we do is trying to scale. Like when we think about checklists and testing, we're trying to create tools to make those scalable. But I think the insight for me has been one that there's no machine learning without humans in the loop. Every step, even though we're thinking about AI as maybe taking over the world, there's always humans involved in creating the models, selecting the data, making decisions, and even consuming the results of those decisions or predictions. And we often forget those humans. We often focus on making the models themselves faster or the training faster, but we don't think about what are the tools that will empower humans to scale better in this overall process. And I think your question is well taken, and that has to be the focus of our work. But really, to me, is about thinking about what is the day-to-day lives of every human being involved in the process, and how can we make that a more productive, happier, more impactful experience. And I think that's where I'm at right now.
Here's another one that I think was really interesting, popping around up to the top actually now, was, and I think it's related to what you said, Carlos, but often you can't put values or human values in quantifiable metrics. So in this case, do you have thoughts on how do we evaluate human values in the models, or somehow capture them in the models?
That is such a great question. And there's other people at Stanford much more qualified than I am at addressing the philosophical and ethical question of how values get translated. But from a practitioner's perspective, and I consider myself in some ways a practitioner, every day we're creating models, we're creating apps, we're creating systems, and they go and do stuff in the real world. And somehow we're hoping that they'll have our values. And we do this in a very ad hoc way. So in a small way, I want to try to figure out how to make it easier for you to transform whatever is in your head or whatever you're hoping for into formalism that machine learning can exhibit. And I think although I might not address some of the most fundamental ethical questions that have been posed in AI, I think there's still a big gap between what a practitioner has to do when it goes to the real world, when we're hacking an app or creating a model and they're using an API, and what they're hoping for. And I think transparency is important. I think feedback is important. I think understanding that is important. And I believe it's possible to create tools to make that easier. And that's what I'm thinking about. But it's hard. It's part of the process, how to make that possible.
So I think this question is related, and I'm going to combine it with another that I think is related. Andrew asks, how do you see the future of ML through the window of these sort of issues? Are large systemic changes in industry and academia needed, perhaps through training methods or process breakthroughs? And somebody else also asked, is the person who's maybe making these kind of tests on the model different than the people making the models? Like, I read it as, is there become a new expert, kind of like how we think of, we have people who do QA in software, not just the people who build the software.
Yeah.
And do we need to be more careful about the models we use and the way we train them?
Do we have another hour, James? These are great questions, and let me just try to give you a couple perspectives. The first one is, you talked about training of people in education. I think this is a great point. When I, let's say, did my PhD in computer science, I got lots of training at Stanford, by the way. I got lots of training on machine learning, on AI or whatever, on algorithms, but very little training on try to understand the human perspective of how these models impact the real world. And typically, computer science students are much more focused on the technical work than on asking those human questions. And I think it'll be pretty impossible for us to completely change the curriculum for a variety of reasons. But I think we need to start exposing more and more our students to the decisions they'll be making in the real world, and helping them be prepared, or helping them figure out what's the team that they need to bring together to answer some of these complex questions. And so in a class that I'm teaching in the spring on the ethics of AI, I hope to not just talk about the methodologies and algorithms, but help spend some time on what are some of these trade-offs and questions that we should be asking ourselves when we're building this algorithm. So I think there's a lot of training that we can do. And as computer scientists, I think there are tools that we can create to help support the decisions along the way. But to fundamentally answer your question, we're in the beginning of a journey of supporting the development of more trustworthy, more ethical AI systems, both in how we develop our education processes, but also how we develop our tools.
Okay, we're almost out of time. I'm going to take one last question, and I'm going to actually cheat and take it out of the chat. Your and my former colleague, Peter at CMU, asks, given that James is moderating, a natural question is, what is the role of HCI to address the problems stressed by the talk, or is this a battle that ML should fight alone? I think I know the answer, but I think I want to hear.
I'm very pro HCI, as you know, James. I think that if you look at the space of computer science, HCI folks often, not of course everyone, but often are the ones who have been having this humanistic perspective to the tools we build for a long time, from the very beginning. And I think some people like me have been lost in the details of the math and forgot the humans involved. And I think that we can all support each other in this journey. So bringing HCI and machine learning together is something that many HCI folks have been doing. Your former colleague, Jeff Hare, for example, and you, James, and many others have done really great work in this space. And I hope to continue to build those collaborations.
That's all the time we have. I think we're going to definitely get Carlos a transcript of the chat and the Slido, because there are so many great questions and comments for him, which I know he'll appreciate. So thank you again, Carlos, for joining us. And thank you to our audience for these thoughtful questions. We'll be taking a few weeks break as the end of the quarter here at Stanford. And then our seminar series will resume on March 30th with Jack Clark, who will be speaking about the 2022 AI Index. And you can register for that talk through the HAI website. And we hope to see you virtually at this. And also note, we'll be having our spring conference in April too. So you can also find that on our HAI website that has a lot of great talks. And there's my AI in the background. Thank you, Alexa. All right. Thank you, Carlos.
Thanks, James. Thanks, audience. Looking forward to interacting with all of you.